Google Cloud Platform manages over 1 exabyte of persistent storage. That's enough to store a billion HD movies. But managing storage for stateful applications in Kubernetes can be a nightmare. Here's what 90% of engineers get wrong. They don't fully grasp the relationship between persistent volumes and persistent volume claims. By the end of this video, you'll know exactly how to design Kubernetes storage using PVs, PVCs, and storage classes to handle even the most demanding stateful workloads. Remember that 1 exabyte number. We'll see why that scale matters when we talk about sharding and local persistent volumes. This is where most people go wrong. They underestimate the importance of access modes in this design. Stop. Think about this. How would you handle a petabyte-scale database?
Let's define the scope. We need persistent storage for a stateful application, like a Postgres database. Functional requirements include storing database files, backups, and logs. Non-functional requirements, high availability, data durability, reasonable I/O performance, and security. Clarifying questions. What's the expected data volume? What are the read-write ratios? What's the acceptable recovery time objective, RTO? What are the security requirements, including encryption and access control? We'll assume a 1 terabyte database with a 70-30 read-write ratio, an RTO of 15 minutes, and the need for encryption at rest. We also need to consider the access modes required for our application: read-write once, RWO, read-only many, ROX, and read-write many, RWX. These determine how many pods can access the storage simultaneously. RWO means the volume can be mounted by a single node for read-write. ROX means the volume can be mounted as read-only by many nodes. RWX means the volume can be mounted as read-write by many nodes.
Let's estimate our storage needs. We have a 1 terabyte database. We'll need additional space for backups, say 50% of the database size, so 500 gigabytes. We also need space for logs, which could be around 100 gigabytes per month. Total initial storage, 1 terabyte plus 500 gigabytes plus 100 gigabytes equals 1.6 terabytes. For QPS, let's assume 1,000 queries per second, with 30% writes. That's 300 writes per second. Each write might be 1 kilobyte, so 300 kilobytes per second write throughput. Bandwidth will depend on the underlying storage technology. Over a year, the logs will consume 1.2 terabytes, so we'll need to plan for growth. This also means we need to consider the cost implications of storing this data, especially in the cloud. Remember this, it comes back later when we discuss volume snapshots for backups. If we have 1,000 QPS, that's 86.4 million queries per day. Each query might read 1 kilobyte of data, so that's 86.4 gigabytes of read data per day. Now that we understand the requirements, let's design the architecture. We'll use Kubernetes stateful sets to manage our Postgres database. Stateful sets provide stable network identities and persistent storage for each pod. We'll define a persistent volume claim, PVC, to request storage. Kubernetes will then use a storage class to dynamically provision a persistent volume, PV. The PV will be bound to the PVC, providing storage to the pod. This architecture allows us to abstract away the underlying storage implementation. We might be tempted to directly create PVs, but that's static provisioning, which is less flexible and scalable than dynamic provisioning. We use stateful sets because they guarantee ordering and uniqueness, which is critical for databases. An alternative would be deployments, but they don't provide these guarantees. Understanding access modes, read-write once, read-write many, is key to making this work. We use dynamic provisioning because it simplifies storage management and allows for on-demand allocation. Static provisioning requires pre-creating PVs, which is less efficient. The secret is understanding how these components interact to provide persistent storage. Here's the twist. The storage class is the key to unlocking dynamic provisioning.
Let's dive deeper into the core logic. When a pod in the stateful set is created, Kubernetes checks for a matching PVC. If one exists, it's bound to a PV. If not, and a storage class is defined, Kubernetes uses a storage provisioner to dynamically create a PV. The storage class defines the type of storage to provision, such as AWS EBS or Google Persistent Disk. Volume binding is the process of linking a PVC to a PV. Claim policies, like retain or delete, Determine what happens to the PV when the PVC is deleted. The default is delete, which means the PV and its data are also deleted. The retain policy preserves the PV, which is useful for debugging or data recovery. Access modes define how the volume can be accessed. Read-write once, read-write many, read-write many. Your interviewer will push back. Why not just use host path? Host path volumes are tied to a specific node, which defeats the purpose of Kubernetes portability. We use dynamic provisioning with storage classes because it provides flexibility, scalability, and portability. The trade-off is increased complexity compared to static provisioning. What happens if the storage provisioner fails? We need proper monitoring and alerting to detect and resolve these issues quickly. For example, if the cloud provider's API is down, provisioning will fail. We can use a retry mechanism with exponential backoff to handle transient errors. The storage provisioner uses the Container Storage Interface, CSI, to interact with different storage providers. CSI uses gRPC for communication between Kubernetes and the storage provider. The CSI driver implements the create volume, delete volume, and controller publish volume calls.
Let's define the data model for our persistent volume claim. We need fields for API version, kind, persistent volume claim, metadata, name, namespace, and spec. The spec includes access modes, read-write once, read-only many, read-write many, resources, requests.storage, and selector for matching PVs. For the Postgres database, we'll use read-write once, since only one pod needs to write to the volume. We'll request 1 terabyte of storage. What's missing from this schema? We should also include audit fields like creation timestamp and deletion timestamp for tracking the lifecycle of the PVC. We also need claim ref to track which pod is using the PVC. We don't need data lineage tracking in this case. The database choice here is Postgres because it's ACID compliant and supports replication. A trade-off is that it can be more resource-intensive than other databases. We considered MySQL, but it's less suitable for write-heavy workloads. The API endpoint for creating a PVC might look like this: post/API/v1/namespaces/persistent volume claims, with a JSON payload containing the PVC definition. The JSON payload will include the kind, API version, metadata, and spec fields.
To scale our storage, we can use local persistent volumes for high-performance I/O. Local PVs are directly attached to a node, providing faster access than network-based storage. However, they're less portable. We can also use volume snapshots to create point-in-time copies of our data for backups and disaster recovery. The Container Storage Interface, CSI, allows us to use a variety of storage providers with Kubernetes. CSI drivers are plugins that enable Kubernetes to interact with storage systems. Remember that 1 exabyte of storage we mentioned earlier? To handle that volume, we need to shard our data across multiple PVs and use caching to reduce latency. We can use Redis as a cache in front of our Postgres database to improve read performance. We use Redis because it's an in-memory data store with low latency. A trade-off is that Redis is volatile, so we need to ensure data durability in PostgreSQL. Your interviewer will push back here. Why not memcached? Redis offers more advanced data structures and persistence options compared to memcached. Local persistent volumes are ideal for workloads that require low latency, such as machine learning or high-performance computing. This is where that 1 exabyte number from the hook matters. You can't manage that scale without sharding across many local PVs. Sharding can be implemented using consistent hashing.
Now let's consider reliability. For fault tolerance, we'll use multiple replicas of our Postgres database. If one replica fails, Kubernetes will automatically fail over to another. We'll also implement monitoring and alerting to detect storage issues. We can use Prometheus and Grafana to monitor storage utilization, I/O performance, and error rates. Alerts can be configured to notify us when storage is running low or when I/O latency exceeds a threshold. What happens if the storage class is misconfigured? We need to have thorough testing and validation in place to catch these issues before they impact production. We'll use a multi-zone Kubernetes cluster to protect against zone failures. We can also use pod disruption budgets, PDBs, to ensure a minimum number of replicas are always available during maintenance. Prometheus uses a time series database to store metrics. Grafana provides a user interface for visualizing the metrics. We can also use volume snapshots for backups in case of data corruption. In summary, we designed a Kubernetes storage solution using PVs, PVCs, and storage classes. The key trade-off is between performance and portability. Local PVs offer high performance but are less portable, while network-based storage offers portability but may have lower performance.
Potential bottlenecks include I/O latency and storage capacity. Next steps include implementing monitoring and alerting, optimizing storage performance, and testing our disaster recovery plan. Remember, understanding these core concepts is crucial for designing scalable and reliable stateful applications in Kubernetes. We used a cache cluster, consistent hash ring, and replication to achieve this.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.